You may not have thought about how the concept of gravitational potential can be useful. But when the gravitational potentials in an area of gravitational field are known, we can predict the behavior of objects. For instance, this can help us understand why it's so difficult for objects to escape Earth. When we were near the surface of the Earth, we had one picture of the Earth's uniform gravitational field. If we look at things from a larger perspective, so that our distance from the Earth can be much greater, then the uniform field picture is no longer true. For instance, think about this. Here's a globe representing the Earth. Before, we imagined gravitational field vectors always pointing downward towards the floor or towards the surface of the Earth. The gravitational field vectors must still point downward because the Earth pulls on any object that's close enough to feel its influence. But now we see that the surface of the Earth is no longer a flat surface, and it's actually curved, and so the gravitational field vectors must point in different directions all the way around the Earth. Let's look at a diagram of these two situations. On the left, we have the picture we drew before, a person in a constant gravitational field at the surface of the Earth. The gravitational field vectors are everywhere the same. They're the same length in the same direction, pointing down towards the surface of the Earth. If we construct a picture of the Earth from this new perspective, we can see that the gravitational field vectors still point downward towards the surface of the Earth, but they're no longer in the same direction. They are arranged radially around the Earth. When we talk about the gravitational field near the surface of the Earth, we have one picture. When we talk about it from any distance, we have a different picture. We calculate the gravitational force between any two objects using Newton's law of universal gravitation. That looks like this. The magnitude of the gravitational force is equal to the product of the uniform gravitational constant and the two masses of the objects divided by the center-to-center distance between the two objects squared. This is an inverse square law, and it shows us that the influence of the Earth on other objects falls off rapidly as we get far away from the surface of the Earth. We say that the gravitational force is proportional to 1 over the center-to-center distance squared. And we write it like that, with a proportional to symbol and 1 over r squared. When we are working with large distances, we have a different way of writing the gravitational potential energy as well. We write U equals negative gravitational constant, mass 1, mass 2, over r. This represents the gravitational potential energy calculated for a single distance, the center-to-center distance between any two objects with mass. If we change that distance, the gravitational potential energy changes. We put the negative sign on the equation because we generally take the zero level for this gravitational potential energy to be very, very far away, in effect at infinity. This means that an object at Earth's surface has a gravitational potential energy in the Earth object system that is less than zero. And then as we get towards infinity, that gravitational potential energy becomes zero. We can imagine what that looks like by saying something like this. If we make r very large, u becomes very small. This gravitational potential energy is less than zero because if you got the object a distance away from the surface of the Earth would pull it back. It takes energy added to the system for the object to be free of the Earth. If you got it far enough away so that the gravitational potential energy was effectively zero, the object wouldn't fall back towards the Earth. Starting from the previous definition of gravitational potential energy, we could write potential like this. V equals negative gm over r, because remember that gravitational potential was the gravitational potential energy divided by a mass. So we've divided out one of the masses in our equation. We could calculate the difference in gravitational potential energy like this. The difference in gravitational potential is equal to the product of the gravitational constant, the mass, and 1 over the final position minus 1 over the initial position. Again, it's negative because we take the zero level to be very far away at infinity. Let's draw a representation of the gravitational potentials around a spherical mass like Earth. This will help us understand the behavior of other objects in the gravitational field of that object. We will again draw isolines of equal potential. Before, when we worked with the ladder analogy, we drew equally spaced lines to represent equal spacings of gravitational potential difference. In this case, as we've seen from the equation, the gravitational potential will decrease as we get further away from the Earth, and that decrease will not be constant for constant changes in distance. So the gravitational isolines that we draw will no longer be equally spaced. These isolines will be concentric circles around the Earth, but they'll represent a 3D equal potential surface that we can imagine being around the Earth at a certain distance from the Earth's center. We can pick a potential interval and calculate the distance at which these equal potential isolines would exist. So let's look at that diagram. On the screen you see a diagram representing Earth with dashed lines of concentric circles representing equal changes in potential. You can see that the distances are no longer equal between different potential lines, and this represents the fact that Earth's influence is weakening as we get further and further away. Before, we drew gravitational field vectors perpendicular to the equal potentials. We need to draw those gravitational field vectors again so we can understand what's happening. Even though our picture of the equal potentials has changed, the relationship between the gravitational field vectors and the potentials has not, and the potential lines has not changed. So we're still going to draw them as perpendicular. I'll draw a few field vectors around the Earth so you can see what I'm talking about. When we're close to the Earth, the gravitational field vector should be longer than when we're farther away from the Earth because the gravitational field is stronger closer to the Earth. The gravitational field vectors always point inward because the Earth's gravitational force attracts other objects towards it, and that's represented by that direction. The gravitational field vectors are always perpendicular to the isolines, and they're arranged radially around the Earth. If we were to draw a representation of equal potential lines and gravitational field for any spherical mass arrangement, it would look similar to this. We might draw different spacings to represent different situations, but the overall picture would be the same. We would have concentric circles of equal potential and perpendicular field vectors arranged radially. As we get farther away from the object with mass, the potential lines get farther and farther apart, and the field vectors get shorter and shorter. In the latter analogy for gravitational potential, the rungs were equally spaced, and the changes in potential in moving from rung to rung were also equal. In this representation, the changes in potential are equal, but the distances are not. So equal changes in distance do not give you equal changes in potential near the surface of a spherical mass. The distances between equal potentials get greater and greater the further we are from the spherical mass, and that represents the weakening of that mass's influence.